Let us discuss avalanche breakdown. A p-type semiconductor material in contact with an n-type semiconductor material forms a p-n junction, in which a depletion region occurs around the plane of contact, as shown in this figure. The width of this depletion region is seen to vary depending on the bias applied at the terminals of the p-n junction. The applied voltage increases the depletion region width for the case of reverse bias. At reverse bias condition, very little current flows through the junction because of minority carriers. This tiny current is called reverse saturation current. Before going through actual mechanism of avalanche breakdown, let us try to understand what reverse saturation current is, because this reverse saturation current ultimately causes the avalanche breakdown. At normal room temperature, there are some semiconductor atoms which absorb sufficient energy from the heat of the atmosphere to release valence electrons as free electrons and create hole behind them. Moreover, absolute n-type or absolute p-type semiconductor cannot be made practically. There will always be some unwanted p-type impurity in n-type semiconductor and some n-type impurity in p-type semiconductor. Because of that, some unwanted holes will always be present in n-type semiconductor, and similarly, some unwanted free electrons will be present in p-type semiconductor. Hence, due to these unwanted impurities and also due to thermal effect of room temperature, there will be some holes in present n-type side, and some free electrons are present in p-type side of the p-n junction. At reverse condition, these holes from n side will flow to p side, and free electrons from p side will flow to n side because of applied electric field. Since at reverse biased condition, the positive terminal of source is connected to the n-type side, and negative terminal of the same source is connected to the p-type side of the junction. Now let us come to the actual mechanism of avalanche breakdown. It is made reversed biased, that means, as I already said, P side is connected to the low potential terminal of the battery, and the high potential terminal of battery is connected to the N side. The junction breaks down, leading to the heavy flow of reverse current through the device. This is because, as the magnitude of the reverse voltage increases, the kinetic energy of the free electrons also increases. The free electron hits the atom at high speed, then generates new electron-hole pair. This newly generated free electron also finds itself in the same strong electric field. Hence, it also gains more kinetic energy and is accelerated further. In this way, the electrons so released further release much more electrons from the atoms by breaking the covalent bonds. This process is termed as carrier multiplication and leads to a considerable increase of both minority carriers, that is, holes and free electrons. This process causes abrupt rise of free electrons and holes in the depletion layer of the junction. That means there is no more depletion of charge carriers across the junction, or in other words, the depletion layer is vanished. As a result, huge reverse current starts flowing through the PN junction. If this current is not limited by external means such as resistance in series, the junction may be permanently destroyed due to excessive generated heat at the junction. This type of breakdown occurring in a PN junction is called avalanche breakdown. Let us see the characteristic curve